So as a review, we looked at oxidation numbers as a way for electron bookkeeping. And here's the reason why. And let me just give you kind of an example of why this is needed. So let's say we have chromium solid plus nickel 2 plus aqueous goes to form chromium 3 plus, not solid, aqueous, plus nickel solid. So if we look at this, we have to balance two things. We have to balance for mass and for charge. So if we look here, we have one chromium. We have chromiums on either side and nickels, so we're balanced for mass. But if we look at charge, we can see on this side of the reaction we have an overall +2 charge, and over on this side we have a +3 charge. So to be balanced, you need to be balanced for charge and for mass. And the only way that we can balance for charge is if we take the charge of chromium 3 and put it in front of nickel, and then we take the charge of nickel and put it in front of chromium. This would then give each side a +6 charge, and so we'd be balanced for charge. But now we're not balanced for mass, and so I have to take the 3 from this nickel and put it here, so we're balanced with 3 nickels on either side, and the same for chromium. Now this way, we're both balanced for mass and for charge. Okay, but that's simple enough. And then again, if we do this for more complex reactions, such as this one, iron 2 plus aqueous plus MnO4 minus aqueous goes to form Fe3 plus aqueous plus Mn2 plus aqueous. So if we look here, we have a problem, and that is our oxygen. Our oxygen is over here, but there is no oxygen on the product side. Okay, and this is specifically because we are dealing with a aqueous solution, so we always have oxygen from water. And so we don't account for that in this reaction, but it is part of it. So we don't have oxygen, so it's hard to balance for mass. We also have to balance for charge. And so these more complex problems are either missing an element like oxygen, or we have, I guess in this case, oxygen is the big one. Then we have to have a need for a systematic way to balance redox equations. And so we're going to do that today. That's our motivation. So we did oxidation numbers. Let's just do some practice with a couple so we remember those. So let's just go through, and I'll give a couple, and let's see if we can do them. So let's do, I'm going to write these out, and we'll take a sec. So we'll do NaH, N2O5, and let's do Na2Cr2O7. So what I want you to do is pause the video and take a couple seconds, write these down, and then assign oxidation numbers like we learned yesterday, and see if you can assign, using the rules, priority given to elements that have fixed oxidation numbers, and then figuring out the ones that have flexible oxidation numbers. So pause the video, and when you have them all, or you get really stuck, then hit play. Okay, so I'm going to put oxidation numbers on top, and then kind of keep track of total charge on bottom. So if we look at water, that's a -2. So we only have one oxygen, so it's a -2. So then from these hydrogens, we need a +1, and that, or sorry, +2 total, because we have a neutral charge. There's no ion charge. The water is not an ion. There's no charge shown, so we have to have a balance of charges. So then this each hydrogen is a +1. But if we look here at this is a metal hydride, this is the situation where the priority goes to sodium, which is always +1, which means in this case, so this is a metal hydride, and this was an exception for hydrogen, just so we remember. Then hydrogen in this case is -1, priority goes to sodium. Now in dinitrogen pentoxide, the priority we always put on the oxygen. Again, the only time oxygen is not given a -2 oxidation state is in the peroxide, HOOH, also written as H2O2. So that's very rare. We don't find that a lot in chemical reactions. So for the most part, oxygen will be -2. So always do oxygen first. We have 5 of the -2, so we have -10. This is a neutral molecule, so I need to get +10 from the nitrogen. I have 2 nitrogens, so each nitrogen must be +5. Now, the harder one, and this is probably one of the harder ones we can do, is where we have 3 different elements, but we know a couple things. We can see that this is a polyatomic ion. I also know that sodium's always +1, that oxygen's -2. So this shows me that this is the chromate ion, which has a -2 overall charge. But you don't have to worry about that too much. It can help. But because we know sodium is +1, we can also use that. So we have 7 times 2 is -14. Now, this is +2, and we have to have an overall neutral charge. So from this chromium, I need to have a +12 to give me no charge. And so +12 would be +6 for each chromium because we have 2. A little bit more complicated. So we can take these to the next step and look at how we can assign these to chemical reactions to see what they're what's being oxidized and what's being reduced. So we have, let's do a fun one, NaH. Well, that's actually not a fun one. Let's do one that is not. Let's see if I have one. Here we go. Okay, let's do this one. Oh, there we go. Let's do calcium solid plus 2H plus goes to form. This is already on. I already did one. Let's do another one. Let's see if we can find one that. Well, let's just do the one that we already wrote down before. At the beginning, that was 2 Cr solid plus 3 Ni 2 plus goes to form 2 Cr3 plus 3 nickel solid. This is a very simple one, and we can use this as a good example of how to approach these. So the first thing you always want to do is just assign oxidation numbers. Metals as solids are always 0. Ions are always their charge. So that was actually super simple for that. Now what I want to point out here is that I'm going to compare my chromiums and say what has happened to chromium. We're trying to figure out where the electrons are going. And so chromium went from 0 to +3. So if you're going up in charge, you're losing electrons, or up in positive charge. So chromium is losing electrons. So that means it is undergoing oxidation. Well, every oxidation reaction must have a corresponding coupled reduction reaction. So hopefully nickel is gaining electrons. Let's check. Nickel goes from +2 to 0. So we've gained 2 electrons to go from +2 to 0. So this is gaining electrons. That's reduction. Okay. So we can write these in half reactions. And so we can have the oxidation half reaction is going to be your reactants. It's going to be Cr solid going to our products, Cr3+. Now, do you need to include the coefficients? Do I need to put a 2 here and a 2 here? Not necessarily. There are reasons for and against it, but for a half reaction, we're really just looking at the charge is changing, and the number of electrons. I'll show you why in a sec, where that might be helpful. If we do the reduction half reaction, that's going to be nickel 2+ goes to form nickel solid. And so we can see here that if we look at what's going on, the nickel is gaining 2 electrons, the chromium is losing 3. And so if we put these coefficients in, so if I have a 3 here and a 3 here, what we're actually seeing, and what we should probably put in here as well, is oxidation is losing. So we're actually having, if we put the electrons in blue, we're actually seeing that for each chromium, we're going from 0 to 3. And so we have 2 of those, so that's actually a total of 6 electrons being transferred. And here, I actually need to write a little, so we have plus 6 electrons goes to form Ni solid with 3. Okay, so the reason why it can be important is that the number of electrons that are used for the oxidation need to match the number of electrons in the reduction. We'll take care of this in more complex balancing, but it's good to know that these two values have to be the same, and that if you have species that have a difference in charge, like +2 and +3, that the total number of electrons for the reaction to occur might be different. So you might have to kind of multiply by a number to get the, so for this reaction, you actually have 2 chromiums and 3 nickels that allow this reaction to occur, which would give us 6 electrons being transferred between the 2 reactants, chromium and nickel. So the other thing that we can describe this reaction, besides making half reactions where we've shown electrons, is to have a half reaction, or we can say what's being oxidized. So oxidation, write this in black. So we can say that, again, what's being oxidized and what's being reduced, we always talk about just the reactants. So we can say that Cr solid is being oxidized. We can say that nickel 2+ aqueous is being reduced. We can also have that we can talk about them as an agent. So we can say that Cr solid is the reducing agent, and we can say that nickel 2+ aqueous is the oxidizing agent. Now, the reason why we change this is that if Cr solid is being oxidized, it's allowing the nickel 2+ to be reduced. Therefore, it is a reducing agent. It is facilitating the reduction of nickel, which is being reduced. Likewise, nickel is the oxidizing agent because it is allowing what is being oxidized, Cr solid, to be oxidized by taking the electrons that are being lost by Cr solid. So it's very confusing. I realize that something that's oxidized is the reducing agent. Something that is being reduced is the oxidizing agent. You got to kind of figure this out, memorize it, and keep those straight, because we will talk about reactants. Again, only for reactants. Can be either of these.